In this video, we're going to talk exclusively about polygons. Specifically, we'll talk about regular polygons, and I'll define those in a couple of minutes. And note that almost everything we talk about in this section is going to be valid for all of absolute geometry, which means no parallel postulate is required. Remember what that means. If the parallel postulate is true, if we assume it's true, we are in Euclidean geometry. But in this case, unless otherwise stated, we don't have to assume that we're in Euclidean geometry. There might be a place or two where we do assume that, but it'll be stated as such. Okay, well, let's start off by defining what a polygon is. An n-sided polygon, the number n has to be at least 3. It can also be called an n-gon. So if you have a 10-sided polygon, you could call it a 10-gon. It's the closed union of a bunch of line segments. And the line segments will be the sides of the polygon. And here's how I'll write them. Let's make a line segment or one side P1, P2 with the bar over it. That's one line segment. And then let's go to the second one, union P2, P3. That's another line segment. And then I'm just going to do union dot, dot, dot. And then the last two sides I will refer to as P n minus 1 Pn. We're not quite done. If you count this up, we only have n minus 1 line segments here. I need one more that will match up Pn with P1. So it's like a cycle all the way around. Pn, P1. That gives us n sides or n line segments all unioned together. So the points that we're using, P1 through Pn, they will be called the vertices. You can think of them as the corners of the polygon. P1 through Pn are the vertices. And also there's a restriction that you can't have any 3 consecutive vertices. No 3 consecutive vertices can be on the same line. They cannot be collinear. If they were, that would not be two sides. It would just be one longer side. And then no 2 sides meet except at the vertices. The corner points, the end points of the line segment, so they're not going to cross in the middle. So let's just draw one up here. What is that? Well, it's got 5 sides. That would be a 5-sided polygon or a 5-gon. And I could label P1, P2, P3. These are just points, the end points of the line segments, P4 and P5. Okay, so that is a 5-sided polygon. All right, well, some characteristics of an n-gon, an n-sided polygon. Well, first, we're also learning some terminology here. 2 sides are adjacent if they share a common vertex. Remember what this double arrow means? IFF, or if and only if. It's kind of a definition here. 2 sides are adjacent if and only if they share a common vertex. So for example, this side here and this side, they are adjacent because they share the vertex P1, sorry. This side and this side are not adjacent because they don't share a common vertex. But every pair of adjacent ones will share one common vertex. All right, part B. any three consecutive vertices, and I'm just going to say pi, pi plus 1, pi plus 2, form an angle that we would call angle, and then we're just going to write pi, pi plus 1, pi plus 2. If we were going to shorten that, we could just call this angle pi plus 1. Now notice that the number I goes from 1 to n, but that n plus 1 you can think of as equaling 1, and n plus 2 you can think of as equaling 2. I'll explain that in the picture in a minute. So an n-gon has exactly n angles. In this picture, we've got all these angles. Here, 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 here. It's a 5-gon, so you have 5 angles. Now, what did I mean about n plus 1? If n is equal to 5, well, what would this angle be right here? It's not P4, P5, P6. We think of P1 as being the P6. So that's why I'm saying that the 6 is, I should have phrased this as P n plus 1 is equal to P1, and P n plus 2 is equal to P2. So this angle right here at P1 is not P5, P6, P7, but it's P5, P1, P2. The indexes kind of wrap around. So it's not going P1, P2, P3, P4, P5, P6, P7, P8, P9, P10, and so on. P6 would just be P1. P7 would just be P2. All right, so an n-gon has n angles. Well, this one I know you'll know the definition of. A polygon is blank if it is completely contained by the two sides and interior of each of its angles. Well, that's actually, that definition is slightly different than the one we saw before. But if this is true, it's convex. Okay, so for example, let's go back to this one up here. If you look at one of its angles and you extend it, let's take P2, this angle right here. So if you extend those sides, and we're looking at this big angle, P2 is this whole thing right here, you can see that the entire polygon is contained in those two sides and in the interior of the angle. And that works no matter which angle you would have picked, whichever one you would have chosen. Okay, and then maybe it's worth drawing another one here. Let's do one that's not convex. We know that's a 5-sided polygon, but we know it's not convex. Why? Because remember, it's convex by our definition in a previous section, if and only if for any 2 points that you choose in the interior of this polygon, that the line segment connecting them would also be inside it. But if we took a point right here and a point right here and connected them, the entire line segment would not be contained inside it. So how does that correlate with this statement? It's convex if it is completely contained by the two sides and interior of each of its angles. Well, let's pick either this angle or this angle. Watch this. That and that. See, it's clear that the entire polygon is not contained inside this angle on this line, or inside the angle. Therefore, it is not a convex polygon. This one is convex. This one is not. Okay, D. What is a regular polygon? Well, a regular polygon is a convex polygon. We just talked about that, with all sides congruent. That means they all have the same length, and all angles congruent. That means they have exactly the same measure. Now, I'll just go ahead and say this. Typically, we're going to assume that all of the polygons we talk about are convex. Unless it's stated that it is not a convex polygon, we will just assume that it is convex. Now, what is the radius of a convex polygon? The radius is the radius of the circle. Remember what that means, the distance from the center of the circle to a point on the circle. The radius of the polygon is the radius of the circle passing through all of its vertices. So I'm going to draw a picture here. I actually already started it. Here we have a hexagon. I'm drawing the circle that touches this six-sided polygon at all of its vertex points. I didn't do a great job there. But what is the radius of this sixagon, this hexagon? It is the radius of the circle. So one way I could draw it is from that distance right there. That is the radius. I'll call it little r. I mean, you could have drawn it anywhere else, but if you want the radius of the polygon, well, you take the center of the circle to get the center of the polygon. And then from the distance from the center of the circle to a point on the circle gives you the radius of the circle, and the radius of the circle is the radius of the polygon. So I could have measured there, or to any of the vertex points. Okay, the radius of the circle, yeah. Okay, this circle that I just drew, the circle C, I'll call it, is the circumscribed circle. It's a circle that goes through all of the corner points, all of the vertex points of a regular polygon. It only happens, it's not only going to, well, not only, but it will work every time you have a regular polygon. Okay, so the center O of the circle is also the center of the polygon. All right, now let's move on to, actually, let me do another one. I probably won't draw it very well. Let's take a square. And let's draw the circle. Let's draw the circumscribed circle for this. It would look something like this. Okay, that's a terrible drawing, but you get the idea. And what would the radius of the square be? Well, the radius, remember what a square is, just a four-sided polygon. So a square is a regular fourgon. The sides are all the same length. This would be the radius from there to there, or from there to there, that or that. Okay, last one, number 3, last one of this video. How do you create a regular pentagon of radius 1? What is a pentagon? It's a 5-sided polygon, or just a 5-gon. So how do we make a regular, all sides the same length, 5-gon that has radius 1? Well, notice I drew a, actually we're gonna use a ruler, protractor, compass. Well, what do we use the protractor for? The protractor gives us the perfect circle. I already have a circle here, and I put a point where I believe the center is, pretty close to the center anyways. And let's just say this is the radius 1. Okay, here's how we can draw the pentagon. You start with that circle with center O and radius 1. Draw a point P1 on the circle. I guess I already did that. This is going to be my P1. And then I draw the radius from O to P1. Now I need to draw P2. Where am I going to put P2? Well, here's where I need my protractor to mark off. Well, let's see. What do I need to mark off? Here's the key. What angle am I going to need right here to draw the second side? Well, every single angle, these internal angles, are going to have to be 360 degrees divided by the number of sides, which is 5 in this case. So 360 divided by 5 is 72 degrees. So what I need to do is mark off an angle and line that up like so. That looks about right there in the center. I'm going to go count 72. Let's see, 20, 30, 40, 50, 60, 70. 2 would be about 70, 71, 72. That's a point. And all I need to do is now, with the straight edge, connect. I don't need to draw it all the way up. I can just draw it right here. All right, so this is 72 degrees, and that gives me the second segment, so to speak. And then what do I do? Well, that would give me P2. Then I need to repeat that process and get a P3. So I'm going to line the protractor up like so, and then go again to 72 degrees, which is roughly 72, roughly that point right there. And then I'm going to connect from the origin like that. I don't need to go beyond that circle. So here's another 72 degrees. I'm just going to estimate the next one. So let's say something like that and something like that. And once you get the 72 degrees, there, and there, we have P3 here, we have P4 here, and we have P5 here. So how do we get the pentagon? You just connect the adjacent points, like P1 with P2, P2 with P3, P3 with P4, P4 with P5, P5 with P1. And that gives us a regular 5-sided polygon, or a regular 5-gon, which happens to be called a pentagon.